Recording. Okay, so hello all my favourite quarantine kids. Today we're going to be looking at first principles. So we're going to calculate the first derivative using first principles. Now before we begin this, I want to just quickly go over how it works. So remember that this is all about calculating an instantaneous rate of change. Now if I was going to calculate an average rate of change, that means I've got an x value down here. We'll call that x1 because it's our first x value. Then over here, I've got y1 because this coordinate represents our first piece of data. Then I've got my second coordinate over here, which we'll call x2, and that represents my second piece of data. Now, normally with first principles, with average rate of change, we find our rate of change by doing y2 minus y1 over x2 minus x1. And we say that that gives us our gradient, okay? Or you can call it your average rate of change. Now, what mathematicians did back in the day is they went through this process and they did a whole heap of these. And they were thinking, well, what happens if I decrease the distance between these two things? Okay, and we want to get it so low that it's almost at zero. What we're really hoping to achieve is an instantaneous rate of change, which means that we don't have any space in between them. So a couple of our brilliant mathematicians went through and said, well, what happens if we change this x and we call this distance between them h? So now, instead of representing my average rate of change, like this, I can say that y2 is my function of x with a little tiny difference in there added in, minus my original function of x, all divided by this coordinate here now becomes x with a little tiny bit added on. So this is x plus h, and then this one over here we're going to subtract x. So if I simplify this formula, it's my function with x plus a tiny difference added in, minus our function at the point that we want, all divided by this one will cancel out that one, crossy crossy, and I'm just left with h on the bottom. Okay, now we're really trying to make that h value as small as possible. So really what we're trying to achieve here is we want the limit of this function, which means we're observing what it's approaching, not what it actually is. Okay, if I can plug a value in and get an answer, that makes me happy, but you're not always going to get an answer straight away. So we want to test the limit for this function as h is approaching 0, because what that really means is that this coordinate is coming in, so pretty much it's just at this one point, and we're testing what the gradient is here at this one point. Okay, opposed to having an average rate of change over 2 points. So this is the formula that we use to calculate using first principles. Now, really all it is an application of substitution. So we did this a little bit differently in class. I'm going to show you a different way today to try and help you, if you didn't fully understand it the first time, maybe you'll understand it better this time. So I'm going to call this fx plus h. Okay, so this will represent this part of my function. So anywhere where I see an x, I'm going to put a bracket only around the x. And I'm going to substitute x plus h in. Okay, if this said just x, I'd substitute just x in. If it said x plus a, I'd substitute x plus a in. If it said bananas, I'd substitute bananas in. Whatever's in this bracket goes in over here where x is. So 4 bracket x plus h squared minus 2 bracket x plus h plus 1. Okay, now I'm going to expand this bracket. Now I'm going to do this over to the side here so I can keep all my working in nice lines because I'm concerned that I'm going to run out of space at some point. So x times x will get me x squared. X times h will get me xh. H times x will get me another term of xh. Plus, and then h times h will get me h squared. Now I can see here that I've got two like terms. So I'm going to add them together. So x squared plus 2xh plus h squared. So that is what is going to be substituted in here because this is what it is when it expands. So now I've got 4 bracket x squared plus 2xh plus h squared bracket minus 2 bracket x plus h plus 1. Now I can expand all of these brackets by multiplying by the coefficient in front. So I'm going to times this one, times that one, times that one, and then over here I'm going to times this by -2, and I'm going to times this by -2. So now I'm left with 4x squared plus, 8xh plus 4h squared minus 2x minus, let's fix that up, sneaky, minus 2h plus 1. Okay, so this whole part here is this yellow part over here. Okay, so now I've got that part. I can substitute it in over here because the next thing I'm going to do is I'm going to subtract that whole function that I started with originally. So now I can write it out like I do for my first principles. So we are testing the limit as h approaches 0 for our function f x plus h minus fx all over h. Now I'm going to substitute this in and I'm going to substitute that in. Now, if you don't put a bracket in around here, around this guy, you are going to get this wrong later. I see this every single year. Someone will not do this, and then that is the mistake that you'll make. So you put a bracket around him so that you know that the minus multiplies all of the terms. Okay, so 4x squared plus 8xh plus 4h squared minus 2x minus 2h plus 1 minus bracket, boom, Miss Cameron, you're a genius. 4x squared minus 2x plus 1. Okay, and now that whole thing, whee, is over h. Okay, so, that was a long one. Now, the next thing I'm going to do, because I'm running out of space, is I'm going to do my cancelling from this line here. Now, the genius of this process is that every single term that's in this bracket will end up being cancelled out. So, it's great. Love it. Okay, I'm going to use purple to do some crossing because who doesn't love purple? If I multiply this through, this will become negative 4x squared, this would become positive 2x, and this would become negative 1. So they'll all change symbols. So this positive 4x squared, boom, he's gone. See you later. Boom. Then I've got this minus 2x here, and then over here I've got this plus 2x. So boom, see you later. Boom, boom. So exciting. Who told you that math was boring? They were wrong. Then I've got this plus 1 and this minus 1 over here. So boom, they're both gone. See ya. See, more exciting than a video game. Okay, so now I'm not going to write this again because I don't have the space, but I will just state what's left. So now I've got is equal to 8xh plus 4h squared minus 2h all over h. Now, what do you notice about this top line? Miss Cameron, they all have a h in them. Thanks, Connell. So now I've got h on the outside. I'm going to factorise a h out of all of these terms. So h on the outside, divide this by h, I'm left with that. Plus, divide this by h, I'm left with this. Divide this by h, I'm left with that. All over h. And now, get ready for it, and boom, cancel, cancel. So now in the next step, I'm going to state what I've got left, 8x plus 4h minus 2, and we're going to let the limit of h approach 0, which means that really we're letting this get really close to 0 so that we can see what happens. And 4 times 0 would make 0, so boom, see you later. So this is equal to 8x minus 2. Now, if you can't remember the process, that's, that sucks, but we'll live with it. State the derivative. You know how to calculate the derivative of this. You know it should turn into 8x minus 2. So make that happen, okay? That's how you get that answer. Okay, so the next part, at what values of x does the gradient of the graph equal to? So the gradient of the graph equal 0. If we're looking for the gradient, that means we're looking at the first derivative. I could call it this, or I could call it d over fx with respect to x. Doesn't matter, they both mean the same thing. And I want the gradient to be equal to 0. Another way of stating this is I want to find a stationary point. Now, when we talk about stationary points, I'm talking about a max or a min, okay? Because that's where my derivatives are going to be equal to 0 because the gradient is 0 at those points. So the hint as well in here is that you're finding values of x, which means that you're not substituting x in, you're finding x. So I'm going to take my derivative from over here and I'm going to let it equal 0. 0 equals 8x minus 2. Take the 2 to the other side. 2 is equal to 8x. Take the 8 to the other side. And I'm left with x is equal to a quarter. So this thing will have a turning point at a quarter. And that's it. Super exciting. Love stationary points.